All right, let's go ahead and work through some of the information necessary to complete the math-related questions on test 4. So this very first question here, folder 4A, question number 1, and it's looking for frequency. Now, frequency typically has sort of a fancy looking F for the symbol here. Formula is nice and simple. You take a number of occurrences or cycles that you're looking at divided by the total amount of time it took for that to happen. So the top number, because it's going to be basically a counted amount, is not going to have any units with it. And the bottom units will be time, typically seconds. So 1 over seconds, so the reciprocal to seconds for the definition for hertz. That's why we get some potentially weird looking units from this. Okay, then the formula itself is relatively simple. If we look at what n is doing, say I take my old value of n and I adjust it by some factor. I'll use the trusty 0.5 that I've used on pretty much all of these. Then the ratio of the new number compared to the old number, if we were to stack these into a fraction, the ends would cancel, we get the 0.5 back again. So that's the reason why I don't specifically need to know what the original number was, but if you wanted to, you could check back in notes and do something similar. Then if the time is unaffected, then old time, new time, if they're put in a ratio together, is just going to be 1. Okay, and then take a number, divide it by 1. Hopefully you're not surprised by the outcome. That's just going to give us the factor back again. So the n was in sort of a plain, boring position in this formula, so nothing really happened when we changed it. Or at least, nothing complex happened. The time, on the other hand, is in a slightly more interesting position. So if we were to take the old time in the question and adjust it by some factor, we'll use 0.5. Then if that's the only thing we're changing, then the number is unaffected. So it would be in a ratio with itself from the new version, old version of 1. And then the new time compared to the old time in a fraction set up as a ratio would give us 0.5. So notice that that's going to end up giving us the reciprocal of the factor, 1 divided by the factor, which for my simple number is going to give 2. For your other decimals, maybe something a little less clean, but that's what calculators are for. Okay, so then looking at the next one. Period is typically represented by a capital T. So think of it as a characteristic time or an important time or time of a cycle, something that happens over and over again. So it's a little bit more important than just a regular little t. Because of the way that we can graph these things and the way that radians talk about rotations in the circle, we can look at this as rotations or repetitions of an object spinning around, bouncing up and down, something like that. We're going to have this 2 pi that shows up from radians. Okay, so that may be a little bit surprising that it was involved here, but again, think about that as being part of a circle, and we can graph these things in a way that kind of looks like a circle. There's also a way to turn it around a slightly different way and graph these in such a way that it looks like a sine function, and 2 pi is important for that as well. All right, then the main part where we're going to end up focusing is that the end of this formula has the square root of m over k, where m is the mass of the object that's moving and k is the spring constant that's providing the force that's moving up and down. Okay, so let's think about what this is going to do. Neither of these variables is in a boring position, right? So even though the m's on top of the fraction, notice that that whole fraction is under square root. Now, technically, we can separate these out and we can look one piece at a time. If we were to set this as a ratio of the new period to the old period, like we're eventually trying to get to with determining the factor of how the answer changes, 2 pi technically goes in a ratio with itself and cancels. And so what I'm looking at, and I can divide this fraction up because there's no addition or subtraction or anything strange going on here, but I can say that this is the square root of m over the square root of k. And that's going to be a little bit easier for splitting these up and seeing how they act independently of each other. Okay, so for m, let's drag this over here where I've got a little bit more space. Let's say that the original mass, could be whatever one in the question, or it could be from some other question, maybe from your homework that you've already done. But I take that and I adjust it by some factor. So like the other ones, I'm going to take it, I'm going to cut this in half. Okay, so then we have to look at what's going on here. the ratio of the new mass compared to the old mass, if we were to stack those in a fraction and reduce, would give us 0.5. So even without knowing the number, I can still figure out what they would be in a ratio with each other. Where I have to be really careful is that these are stacked under a square root, right? Okay, then if I look at k, if k is the same as it was before, if this part's not changed, so again, I could look at, this one says 28.86, I could stack that in a fraction with itself and it would give us 1. Now, to be clear and to follow the formula, technically it's a square root of 1, but I think you can see that's not really going to do a whole lot. So this is going to give me the square root of the factor. So one of these questions where we don't just cleanly get back the factor or some reciprocal or exponent to it, we've got the square root this time. Okay? And so if we were to double check what that's going to make, go ahead and take 0.5 and then take the square root of that, then we get 0.7071. Okay, and then if we look at k, it's also under square root, but it's in an even more interesting position because it's under square root that's under the bottom of a fraction bar. So let's see what that's going to do. So let's say we had some spring constant, we adjust it by a factor, so I'm going to cut it in half. And we want to see how that's going to plug into here. So if we're only taking a question, we're only modifying the spring constant, then the mass isn't changing, then we'll have that in a ratio with itself of 1. Okay, so square root of 1, then you can see where that's not going to really change anything. But k is going to be interesting because, again, not only is it under a square root, it's under a fraction. So I'm going to have square root of 0.5. Okay, so then this is going to end up giving me 1 divided by the square root of 0.5, which is the factor I plugged in. If we run that through a calculator, not only is it the reciprocal, but it's also the square root. So keep in mind that this is going to give us 1.4142. There's a square root involved, so that's going to keep going forever. That's probably enough digits for us to see what we need. Okay, then not very often that we're going to deal with gravity that's not just Earth gravity, but this does specifically say calculate the gravity on an unknown planet. So technically, this takes the period formula from a pendulum. So if we knew how a pendulum was moving, then we could plug in gravity and determine the length. Or if we know the length, then we could work backwards and calculate gravity, which is the strange question we've got on this one. So I've shown in a different video or in previous notes how to resolve this formula. You can also see a rough outline of that here. But what we're looking for is that the gravity, if we're looking at a pendulum to determine gravity, is going to come from 4 times pi squared times the length of the pendulum divided by the period of the pendulum squared. Now, coincidentally, pi squared is actually relatively close to Earth gravity, but that's pure coincidence. So no special meaning or anything there. Okay, and so if we look at what this is going to do, then keep in mind that we're looking for a ratio of a new answer compared to an old answer. So these things that are constants are basically just going to cancel out from each other. So really what I'm focusing on and what's going to make changes between different sets of numbers is really the length of the pendulum divided by the period squared. Okay, so let's see how these different variables will make changes. L is in a nice, easy position to look at, so I think you might be able to see what this one's going to do. But let's work it out and see. So if I take the original length, whatever was in the question, and then I modify that by a half, then thinking about plugging this in and what the answer is going to do, I would have a ratio of the new length compared to the old length of 0.5. And then if I kept the same period as before, then I would have a ratio of the new period to the old period is 1. And then on the bottom, technically, I've got 1 squared. So that's just going to give us the ratio back again. Okay, and then if we look at what happens if we change the period, then, that seems to be in a more interesting spot. So let's say that I take the old period, whatever it was, and multiply it by some decimal to change it. Okay, then in this case, if I'm only changing the period and I'm not looking at the length, then the ratio of the new length to the old length would be 1. And then the ratio of the new period to the old period is 0.5 for the factor that I've chosen here. Okay, but we can't forget that in the formula itself, it has t squared. So that pops up because originally this gravity was buried inside of a square root. So we had to square all of these things outside of the square root in order to get that free. So you can kind of see that in some of the scratch work here. Okay, so then as we're working this down, we're going to get 1 divided by the factor squared. So taking 0.5 and raising it to an exponent 2, squaring that's going to make that 0.25 or 1/4. And then 1 divided by that means I'm looking at the reciprocal. And so for my example, that's going to make 4. Okay, and then the last one from this module folder, so 4A number 10, is the Doppler effect. So as a moving source of sound produces sound and somebody is observing, they're going to hear higher or lower frequencies compared to what's actually being produced. So you can think of it almost like the sound is being brought to you more quickly or more slowly depending on how you and or the objects are moving, and so it causes your ear to detect a different frequency. So because this is a new frequency, then we have F prime. So a little tick mark just means that it's been affected in some way. We could also have said F1 and F2. So made this a 1 and that a 2. It's up to you. So what happens is you have your original frequency, whatever it was before, and then you're multiplying it by essentially some scaling factor. So we have the velocity of the wave or of the speed of sound divided by the velocity of the speed of sound, and then technically plus or minus, depending on whether it's moving towards you or away from you. So I'm going to leave that as plus or minus for now. And then, so these two are intentionally the same thing. And then what we have here is the velocity of the source. So if this was a train blowing the whistle, if this was somebody somehow running and playing the tuba, whatever, then the speed of the source moving would go in here. So notice that we use the same thing intentionally twice here. Okay, then kind of depends on what's changing here. The only thing I think that's really easy to tell what's going on is the original frequency here. So if the original frequency is adjusted by some factor, so say whatever it was, we took it and we multiplied it by a half, then what will happen is we will have 0.5 here, and then that's going to multiply. So if none of these velocities have changed, then this giant fraction, whatever this group is together, would be stacked over itself, and then everything from there would cancel. So this would be a ratio of what? So the frequency on its own is going to change predictably. Whatever factor you multiply it by, it's going to change the answer by that factor. Okay, and then this is where we have to be kind of careful. So we've seen this multiple times. If you have addition and subtraction in the middle of your formula, if you have multiple formulas chained together, then it's really difficult to change one little piece that's buried in the formula and get a reasonable answer. So if I change only the velocity of the sound, so somehow I could change the speed of sound. Technically, if I could change the temperature outside or the temperature in a room, I could make that happen. Then that would, give us a predictable answer on the top, but then I'm going to have no idea what kind of answer I'm going to get if I start adding and subtracting things with that, because multiplication and addition and subtraction are really just not compatible with each other. Now, technically, if I multiplied all the velocities by some factor, then in the end, those things can be factored out, and we could see what that was going to do. So, like I said, if you change one velocity, it's not going to make sense. But if I change the velocity, let me move this over a little bit. If I change the velocity of the sound and the source, sorry, my pen's acting up today. By, again, let's use 1/2 because that's what I keep using. So 0.5 times whatever it used to be. then what's going to happen? Okay, so the frequency is not adjusted on this one. And then technically what would happen is, because this has its own factor in it, we'd have 0.5 up top. And then both of these things would have a 0.5, and then technically they could factor out kind of like the opposite of distributive property, and we'd get 0.5 again. So notice from this that we get the factor stacked on top of itself, and we get 1. And so that would mean that it does not change. Okay, so moving into 4b. The Coulomb force is given by kind of a scary looking equation. It's got a bunch of pieces to it, a lot of scientific notation. But the Coulomb force, so F for force and often a C for Coulomb, is equal to this special constant K, which is roughly 9 times 10 to the 9. Some ugly units, but those are designed to cancel and give typically newtons left over as an answer. And then you have your first quantity of charge, so Q1, multiplied with your second quantity of charge. So if we've got two groups of charges, and then divided by the separation distance squared. Okay, then thinking about what this formula is going to do, if we make some changes, we find a new answer and try to compare the two. Well, if we're going to set these in a ratio and find out the factor with the change, then K is going to end up canceling itself out. So what I'm really looking for is Q1, Q2 over R squared. Okay, and so let's think about how these things are going to change if we start playing with some numbers. So let's say that I change just Q1 or Q2. Okay, then if I take one of these and multiply it, there's not addition or subtraction in the middle, so this is actually still going to be okay. Often changing one piece of information causes an issue, but this time it doesn't. But let's see. So if I take that, let's say I cut one of these in half, again for 1 or 2, then it doesn't really matter which one's which. In fact, let me be a little bit more explicit. Let me say we'll do 1 and then we'll do 2, and just to really prove that this is true. If I take Q1 and I cut it in half, then I'm going to end up plugging 0.5 for this ratio. Q2 is unaffected, and then the radius is unaffected for the separation distance. That's at 2. And so I end up just getting the factor back again. And then if I were to explicitly show Q2, so let's pick a new color though, then Q2 is changed by a factor of a half, then we'd end up with 0.5 here. So it technically just changed the order, but it's all multiplication in this case for the top part, so that's not going to hurt anything. Okay, then let's say that we changed Q1 and Q2. Then I think you might see where this is going. We've got two numbers that we're going to plug in and make changes for. So for Q1 and Q2, then I'm going to have 0.5 for the first one. I'm going to have 0.5 for the second one. And then on the bottom, I'm going to have 1 squared. So notice that this ends up being the factor squared. And that for me is going to end up being 0.25. Okay, and then the last thing that we can reasonably mess with here is the separation distance. So let's say that r, this radius for how far apart they are, is adjusted by some factor. You want to pay attention to where r is at. So if q is unaffected, if the other q is unaffected, what I'm looking at is 0.5 on the bottom of the fraction, but also with an exponent. And so that's going to give me 1 over 0.5 squared. So 0.5 squared is 0.25, and then 1 over that to take reciprocal is ended up making 4. Okay, so then a little bit later on in the same section, we're going to look at a simple case of Ohm's law. So Ohm's law says that a potential difference is equal to a current multiplied by a resistance. I for current, similar to the word intensity, comes from French or Italian, I forget. If you've ever been shocked, then intensity definitely makes sense for talking about current. Just in English, the letter seems weird, but like I said, it comes from a different language. Okay, so it says that in this question we are given current, we're given resistance, so we're just looking at the base version of this formula. We don't need to resolve anything. And so I think it's going to be relatively easy to see what's going to happen here. Let's say that the current is affected by some factor. I'm sure you know which one by now. Then we're going to take, oh, there's that glitch again. So 0.5 for my factor, you'll have, whatever numbers 0.755 or whatever you end up with. And then the resistance here is unaffected, so we end up just getting the factor back again. Okay, and then looking at the resistance, if the resistance is adjusted, so we take it and we multiply it by something, which, like I keep saying, you can manually change in the question, work it again, divide the new answer by the old answer, and it'll work through the same stuff. But I want to show the formulas a little bit better here, show the reduced math versions for solving these. Okay, but if we look at the variables, I for current is not being affected, so new current to old current is a ratio of 1. Then new resistance to old resistance is in a ratio of 0.5, and you might have seen it coming, but we just get the factor back again. Okay, then we've got two more in this section that we're going to take a look at, and then we're going to switch to 4C. So this one's 4B still. It's question number 9 from our notes before. Okay, and so we have a version of the power formula. So sort of the simple version is P equals IV. But if we take what V is equal to and plug into that, this is something that I showed in a previous video or in different notes. But we get that P is equal to I squared times R. Okay, then we want to pay careful attention to what this is looking for. It says we're calculating the resistance. We're looking for R. So if we're looking for R, then this I squared has to move away. So we're going to divide to get rid of it. And then that's going to give us a formula that the resistance is equal to the power divided by the current squared. Okay, so then now let's see what these variables are going to do. If P is adjusted by some factor, then we take the old power, whatever it used to be, multiply it by the number for how it changes, and then we can look at this formula. P is at the top of this fraction, doesn't have a square root or addition or an exponent or anything fancy, so we end up just plugging in that factor. Then on the bottom, if we're only changing power right now, then the current is in a ratio new current to old current of 1. Technically that's squared in the formula, but that's not going to hurt our factor. So we just get that back again. Okay, then if we look at the current, so this one's in a bit more of an interesting spot. If we take this current, we multiply it by some factor to adjust it, work a new version of this question, and then compare those, then it'll go through a similar process like this. So if the power is unaffected, then the ratio is 1, it's left alone. Then the ratio of the new current compared to the old current is 0.5. So same thing that we would get if we were to stack these in a fraction and reduce. Then we get 0.5 here, and then squared because of the formula. So it reduces down 1 over 0.5 squared. Okay, so 0.5 squared, we've already, I think, used this a few times today. It gives us 0.25, and then 1 divided by 0.25, or the reciprocal of that, is going to give us 4 for this question. All right, then last one for the group. So this finishes up module folder 4B. Then we're going to look at that same formula again. We've got that P is equal to I squared times R. So if you notice and you look at your different things that we're using and the information we have compared to what we're looking for, you can look through these formulas. The only one that has a combination of I, R, and P, it's out of order, but that's fine, is this formula. Now, this time, because we want the current, we do have to work a little bit harder to rearrange this one. So if I'm trying to get this thing by itself, then I want to look at the stuff that's around it that's in the way. So I want to do the easiest things that I can. I don't want to mess with that exponent until I absolutely have to. So in my first step, I'm still going to have I squared, the current squared here, but this is now equal to P over R. Okay, and then I want to sort of start over and evaluate my position and see where I'm at. So I'm still looking for this current. It still has this exponent. I wish that was gone. So then I can take a square root of both sides and that'll take care of it. And then for simplicity for later, square root of a fraction is the same thing as the fraction of the square roots. So I can say that this is a square root of P over square root of R. Okay, there wasn't multiple fractions and there's no addition or anything else funny going on, so this works out just fine. Okay, so now I want to see what these things are going to do. So let's say that I take the power and then I take that number and I multiply it by a factor. So, no surprise, we'll use a half. Then I want to pay attention to the fact that this plugs into the top of my fraction, but then that's under a square root also. So that's going to be important for the answer. On the bottom, we've got a 1 technically under a square root, so nothing's going to happen there. So what I'm looking at then is I've got the square root of 0.5. So we've seen that already a couple of times, but that's going to turn into 0. Let me fix that to actually look like a 0. 0.7071. Okay, and then R, it's resistance here. So if I take R and I adjust it, multiply it by some factor to rescale it. So we'll use 1/2 here. I'm also going to try to fix my handwriting. Might be a lost cause, but I'm going to try. Then the power is not changed, so still just 1 there and square root of that because of the formula. And then where we have to be careful is on the bottom, we've got 0.5 or whatever your factor is, and then square root of that. Okay, so the 1 up top is going to simplify down to just be a nice clean 1. Okay, and then on the bottom, we're going to end up with the square root of that factor. So you're looking for the reciprocal of the square root of the factor. So definitely, an interesting thing here. Although I think we've actually seen this combination already today. Technically, we're taking the 0.7071, taking the reciprocal there. Then this is going to end up giving us, like I said, I think we've already seen this before, 1.4142. I think I could just barely squeeze that in, 4142. Close enough. Okay, and then now 4C. So we just have a few of these to work on, and then that's it for this group. Okay, so a little bit more going on with this one, just because it's a set of parallel resistors. Okay, so that's something we have to pay attention to, because with parallel resistors, you've got basically one source of power, one potential difference that can split and go multiple directions. So it's like having multiple circuits running next to each other, which is where that word parallel comes in. Okay, and so because some of the current can go around in one direction and some more of the current can go around in another direction, you've got multiple current loops, and your total current running through the system for your circuit is going to come from just adding up each of those individual contributions. So I total is going to come from I1 plus I2. Okay, so in general, if we were to look at one specific resistor, then the current is going to come from resolving Ohm's law and saying that current is equal to potential divided by resistance. So think of potential as how much it can do overall, and resistance is how much is working against it. Dividing those two will tell us eventually what that thing does. Now here, I didn't put any subscripts on this, because this is just in general. It's taking Ohm's law and solving it first. But we can take this information and we can plug it back into here, and we can use this for any individual current in this parallel circuit. So I total is going to be, for I1 is going to be V1 over R1. And then for I2 is going to be V2 over R2. Now, what's nice about a parallel circuit is that the potential, the V, is the same because there's only one source that's pushing current around multiple places. So specifically, V1 is equal to V2, and it's just whatever potential is on the full circuit. Okay, so what that does for us here, I know I'm using a lot of colors for these, but we get some voltage that affects both of these the same way, and so it can be factored out, sort of like the opposite of distributive property. Now, because I took the V away from this, I can't just leave R. I have to remember it's in the bottom of a fraction. So I'm going to have 1 over R1, so the first resistance, plus 1 over R2, which is the second resistance. Okay, so kind of a lot was happening there. We have this formula now, and yeah, I'm gonna have to draw some kind of long lines to make connections from these, but we can still make this work. Let's say that I'm looking at just the potential. So the potential is adjusted by some factor. Then that means that I'm going to have 0.5 out front of this, and then the ratio of the sum of these reciprocals of these resistances. That's a lot of words. But if I'm not changing the resistances at all, then I'm not going to be changing the fraction flipped over or the sum of these or anything, so that's going to be in a ratio of 1. So look at where V is. V is in the most unaffected place. It's outside basically of everything else. And so I multiply it by some factor, then my answer is just going to change by that factor. So for me, 0.5. Okay, then if I change one of these resistances, especially since it's a reciprocal and there's a sum here and then it's multiplied by something later, then I hope it makes sense that changing one resistance is not predictably going to give you an answer. You have no idea what's going on. And especially if these are different values for parallel resistors, then again, we have no idea really what that's going to do. However, if R1 and R2 are changed together by the same factors, we change both of those, then as it turns out, we can still do something with this. So potentially it's not going to be what you're thinking, but we can still work with this. So the potential is not going to be affected. It's going to be in a ratio new voltage divided by old voltage is going to be 1. Then what's going to happen is each of these resistances is going to have that same factor in it. And so we're going to end up with 1 over the resistance, or sorry, 1 over the factor factored out of these. And so it's a little bit weird to see, but we're going to end up with 1 divided by 0.5. Think about it. If the r's are in the bottoms of these fractions, then that's how they're going to pull out from these. And then technically, if we left space for where these are at, then we'd have a 1 at the end. We don't technically need that, but we can use it if we want to. And then from here, we end up with just the reciprocal, so of this factor. Let me fix my handwriting. So 1 over the factor. And so for my nice clean number, that's going to have given us 2. So that's kind of an interesting one. Like I said, if there's only one resistance change, you have no idea what it's going to do. But as long as both of them are, then we can consistently get an answer. But because it's the reciprocal to the resistances, we end up getting a reciprocal to the factor. And so it kind of flips and goes another way. Okay, then just a few more. We're going to look at 8, 9, and 10 to finish out this section. So from module folder 4C, again, question 8 from the example, we have a nice clean formula for what we're looking at here. We don't have to worry about the units on this one. We're going to presume that any adjustments and conversions have been made. And technically between different versions of the question, then most conversions end up canceling each other out anyway. So what I'm really looking at is just this formula that says that the current running through a wire multiplied by the length of the wire multiplied by the magnetic field that the wire is in will give me the force for how the wire is going to push and pull. Okay, so all of these are in a line and then just multiply it, so you probably can see what this is going to do. If we have current, oh, stop it. If we have current and we adjust it by some factor, then that's going to give us a ratio of new current to old current of whatever this factor is. Then if the length is unaffected, then that's going to be ratio of 1. If the magnetic field strength is unaffected, then that's going to be ratio of 1, and that's just going to give us the factor. Okay, then let's say that I change the length of the wire. So whatever length of the wire we used to have, we took some question, maybe even this one, and then we took just that one number and we multiplied it by something. So your new question, your potential test question is going to have something probably not as nice as 0.5, but that's okay. Basic process is the same. The current is not going to change by any factor. We're only changing one variable at a time unless the question very specifically says so, that we're changing more. Then here we're changing that length. So ratio of new length to old length is just the factor. The magnetic field strength is not tampered with, so we just get that number back again. And then technically, it's the same as before, just out of order. Multiplication doesn't care. So here we also get back our factor the same as it was. Okay, then last one in the group. You shouldn't expect anything different though. So magnetic field strength is adjusted by multiplying by some decimal number. Then that's going to get smaller. We want to see how it's going to affect the answer. Well, if the current's not changed, and if the length isn't changed, and only the magnetic field strength is changed, then once more multiplying all the same things together, potentially out of order, but doesn't matter. We just get that factor back again. Okay, so that was number 8. Here we've got number 9. And okay, so this formula is an interesting one because it has some constants and some kind of ugly numbers in it. You can also see in the scratch work if you can either kind of squint and look at my tiny example here. If you look back at your old notes, which is hopefully on, at least a quarter of a sheet of paper. But the magnetic field strength here is equal to mu0, which is just a special constant number, multiplied by I, which is the current running, and then 2 pi times the radius or distance away. So the 2 pi is the fact that we're looking at something that's consistent around a ring around the wire. So 2 pi r is the circumference of the ring that we would be looking at a certain distance away from the wire. Now, the nice thing about this is, because we're going to make a small change and compare the new answer to the old answer, then technically mu0, mu naught, is a special number and it cancels away. 2 pi is, again, some other special number and it cancels away. If you decide to be fancy with it, technically you can cancel 2 pi as part of mu naught and then cancel the leftover constant from there. But in the end, what we really need from this, if we're seeing how the answer will change from making, small little differences on the numbers, is we're really looking at the ratio for how the current has changed divided by the ratio for how the separation distance or radius has changed. Okay? So the current ought to be easy to see what's going on. It's on the top of the fraction, which usually makes that simpler to deal with. So let's say that we have the current adjusted by some factor. So we'll say 0.5, because why not? Then the new current compared to the old current will have a ratio of 0.5. And then if the radius is unchanged, the distance away from the wire is unchanged, then it's going to have a ratio of 1. So that's going to give us whatever factor back again. Okay? Then the radius, because it's on the bottom of this fraction, is going to be a little bit more interesting to look at. So I take my original radius, my distance away from the question here, and I multiply it by some factor to scale it up or down, depending on what we decide to do with it. Then the current is not going to change, just the radius is. So I'm going to have 0.5 on the bottom of this. Or, again, it could be any different factor. Typically, these are ugly 3-digit decimal numbers. I was using 0.5 to make the examples a little bit cleaner. But this is going to end up giving the reciprocal to my factor, whatever it happens to be. It's probably going to be ugly, but that's okay. It's what calculators are for. Mine is nice. It's just going to give us 2. Okay, and then last one to round out the section here. So magnetic flux, unfortunately, we have a lot of different concepts that we're looking at here, and so we get to some new Greek letters that we don't see very often. But that's our symbol for magnetic flux, kind of like a circle with a vertical line through it. It's equal to the magnetic field strength of a certain area running through a certain area. So I should say in a certain space running through a certain area. So basically how the field lines pass through the surface of something. Okay, well, I mean, that's really simple, right? And it's even just the first 2 letters of the alphabet, technically out of order, but you could swap those if you wanted to. In fact, let's look at them in order. Let's look at A first. I'm not giving you any kind of shape, so we're not doing pi r squared or length times width or 1/2 base times height for a triangle or anything. We're just somehow we know the area. And so if this area is multiplied by some factor and it's changed, then if the magnetic field strength is not messed with, then the ratio of the new field compared to the old field is going to stack in a fraction to cancel to make 1. So in this case, we like taking 1.43 on top of 1.43. And then the area taken 0.5 times this number divided by the originals just gives us 0.5 again. And so there we see our vector. Okay, and then last one in the group here, last variable even in the group. If B is changed, it kind of looks like a disconnected 13, but that's meant to be a B. In fact, that's going to bother me. Let me fix it. All right, better. More or less. All right. Then multiply that by some factor. Then in this case, we've adjusted the field strength by that number, but the area is unchanged, and we get back the factor. Okay, and then for test 4, that should do it.